got an integral up here on the board. I'm saying that E is going to be the region between z equals root x squared plus y squared and x squared plus y squared plus z squared equals 4. And I want to integrate over E z squared dv. Now, you might guess that we're going to switch to spherical coordinates. There are a couple reasons for doing that. One, this is in the video lectures for switching to spherical coordinates, okay? But more importantly, I recognize that both of these boundary surfaces are just constants in spherical coordinates. This is a sphere of radius 2, so its rho is equal to 2. This is a cone, because that's essentially saying z is equal to r. And we looked at that before. If I look at a constant theta half plane, what I see with a cone, I'm just going to draw just a cross section here. Normally this would be z and this would be r, and there's my phi value. But z is equal to r. So that tells me that tangent of phi is z over z, or 1. Phi is going to be pi over 4. And I know that that does give me the equation of a half cone, which is exactly what I want. Obviously, z over z is not 1 when we're at 0. However, the origin is included in the graph of this, and the origin is included in the graph of this, so they are equivalent. Okay, so I think it makes sense to switch to spherical coordinates because of that. Okay. So notice the region that we have looks something like this. We've got a cone capped by, well, I don't know, a scoop of ice cream. Now, I've exaggerated the scale on the scoop of ice cream for a couple of reasons. Realistically, this is part of a sphere that's centered here, so the curvature would be much less. But if I actually draw it to scale, it becomes difficult to distinguish between the curve that's the scoop of ice cream and the curve that's the back part of the cone right here. So I like to exaggerate. The other reason I like to exaggerate is because I like ice cream, and having a bigger scoop of ice cream just makes me happy. So I'm happier doing the problem if I'm thinking about lots of ice cream. Okay, so I'm going to need to figure out what my limits of integration are. I'm going to need to write my integrand in terms of spherical coordinates, and I'm going to need to remember that dv is rho squared sine phi d rho d phi d theta. I'm going to go ahead and write that right now so I don't have any chance of forgetting. The other bits we have to do a little bit of work on unless we've accidentally memorized already what this is. Now, I know that z is not only a rectangular coordinate, but it's also a spherical coordinate. So that's really nice because it shows up in this triangle that helps me to convert between spherical and cylindrical coordinates. So if I look here, I can see that cosine of phi is equal to z over rho, and that means that z is equal to rho cosine phi. So z squared will just be rho squared cosine squared phi. So now we need to figure out our limits of integration. I like to draw myself what I see in a constant theta half plane, where there's the z-axis, there's the xy plane, which is understood that it's coming out of the board like so. And what I'm going to see is this would be right here at the origin. So what I'm going to see in that half plane is something that looks like this. I've just drawn in that dotted line to show that's where the cone and the sphere meet. Okay. All right. So if I'm solving for the rho values, that's going to be a function of phi. Probably not a function of theta, because I can see, definitely not a function of theta, because I can see that I have rotational symmetry. Okay. So I get exactly the same picture in every theta half plane. So if I draw in some constant phi rays, again, that's just the intersection of a cone with the half plane, I can see that for each value of phi, I'm in this region as rho varies from 0 to the rho value of the sphere. And that's true even when I hit this boundary value here, I still go until I hit the sphere. So my rho values are going to be going from 0 to 2. I can see my phi values are going from 0 to the phi value on the cone, which we said was pi over 4. And if I'm getting this whole cone, we're rotating all the way around. So theta is going to go from 0 to 2 pi. So we've got our integral set up now in spherical coordinates. Before I'm ready to integrate, I generally want to multiply this stuff together. So I can say this is from 0 to 2 pi, 0 to pi over 4, 0 to 2. Looks like I've got a total of rho to the 4th, and then cosine squared phi sine phi, d rho, d phi, d theta. Okay, so integral 0 to 2 pi, integral 0 to pi over 4, antiderivative of rho to the 4th is just rho to the 5th over 5. I know I'm going to be evaluating that between 2 and 0. Then I'm multiplying by cosine squared phi sine phi and integrating d phi and d theta. So let's see, when I plug in 2, I'm going to get 32 over 5. When I plug in 0, I'm just going to get 0. So this becomes 32 fifths. That's a constant, so I'm going to pull it out. So 32 fifths, integral from 0 to 2 pi, integral from 0 to pi over 4, cosine squared phi, sine phi, d phi, d theta. Looks like we need some more space. Okay, so let me just copy that down over here. 32 fifths, integral from 0 to 2 pi, integral from 0 to pi over 4, cosine squared phi sine phi, d phi d theta. Looks like we want to do a u sub. Let's let u equal cosine of phi. Then du would be negative sine phi d phi. So I'm going to need to introduce a negative sign counterbalanced with a negative on the outside. And of course, this negative sign is just going to get absorbed with the d phi to become part of the du. So we will have negative 32 fifths, integral from 0 to 2 pi. We're integrating from cosine of 0, which is 1, to cosine of pi over 4, which is root 2 over 2. And we're integrating then u squared du, and then we'll integrate that with respect to theta. So negative 32 fifths, integral 0 to 2 pi. This is going to become u cubed over 3, evaluated between root 2 over 2 and 1. And then we still have to integrate that with respect to theta. So negative 32 fifths, integral from 0 to 2 pi. When I plug in root 2 over 2, root 2 cubed is just 2 root 2, over 2 cubed is 8, and of course I can cancel, so that's going to give me root 2 over 4. All of that's still over 3, so that becomes root 2 over 12, minus, when I plug in 1, I get just 1/3. And then we've still got to integrate that with respect to theta. But notice my integrand now is just a constant. And when I get integrate a constant, I get that constant times the length of the interval. So we're going to have negative 32 fifths times root 2 over 12 minus 1/3. I think I'm just going to write that as minus 4 over 12, okay, times the length of the interval, which is 2 pi. Okay. Now, if I look here, 4 over 12 is bigger than root 2 over 12. So this is a negative number, which will cancel with that negative there. So I think what I'm going to do is just use that, absorb that negative to switch the order of the subtraction. So I can rewrite this as 32 fifths times 4 minus root 2 all over 12 times 2 pi over 1. And let's cancel what we can. Looks like I can cancel a 2 to get a 6 there. So that's going to leave me with 32 times 4 minus root 2 times pi all over, oh, I can cancel one more thing. Sorry, I can cancel another factor of 2. 16. Okay, so that's going to give me 16 times 4 minus root 2 over pi all over 15. Okay. You'll notice that is a positive number. Okay. This was just given to us as an integral. In theory, they're allowed to be negative, but if you remember, the original integrand was z squared. So I knew that the integrand was not negative, so I knew I should be getting a positive answer, and we did.